What are the other components while developing entangled states? These are light, classical or quantized. We have atoms, cavities, detectors, beam splitters, mirrors. So these are the tools with us to generate entanglement among uh, various atoms or cavities or the things. What we discussed so far, we discussed atom field entanglement. We have discussed atom entanglement. We have discussed field entanglement. We have discussed generation of GHZ state, fixed number of photons, W states. We discussed on the continuous variable using beam splitter. We discussed continuous variable entanglement. We discussed the entanglement generation among quantum dots and entanglement generation among the surface plasma. So these are the stuff we have discussed in our two lectures. Now there is a question. Question is that no quantum system is in isolation. Quantum system interacts with the environment. Every quantum system interacts with the environment. So when it interacts with the environment, the entanglement gets decreases. So we don't know what is the behavior of entanglement when the state interacts with the environment. In the first few lectures, there was some discussion why a qubit, when a qubit interacts with the environment, what happens with a qubit? This interaction of system with the environment is unavoidable. It is environment is there, whether it is vacuum. Vacuum is also an environment. Environment is there. System always interact with the environment. We cannot avoid this interaction. So we have some ways to measure it. So we have some ways to measure the quantumness. We have to ways to measure the entanglement, and we have some mitigation techniques. We have to improve this entanglement. So interaction of system with the environment induces decoherence. Decoherence in loss of coherence. This decoherence have some local phenomena, local dynamics. If it is because entanglement is among two particles, so this decoherence is on individual particles as well as combined systems. So this local decoherence leads to the dynamics, local dynamics, single particle dissipation, diffusion, or decay, or it may have global dynamics. Global dynamics mean on the entanglement system. So decay, we know that single atom decay or single particle decay exponentially. It is a decay, exponential decay, asymptotic behavior it shows. But what about entanglement? Entanglement decay in the same way as the single particle, as the atom decay or photon decay or some other quantum state decays, whether entanglement decays in the same way? Answer is no. Entanglement behavior is different from the single particle decay. We may have sudden death of entanglement. Entanglement may disappear at some finite time. While we say that decay of atom, it decays at some infinite time, it is exponential decay. But in the case of entanglement, it is different. Here, schematic shows that when a system, let's say it is a two-level atom, excited state and ground state, this system interacts with the reservoir. Simplest reservoir, we consider it is vacuum. Vacuum means only the vacuum fluctuations. When this system interacts with the reservoir, then what happens? If the atom is in ground state and reservoir, there is vacuum in it, there is no change because both are in lowest energy state. Atom is lowest energy state, reservoir is in lowest energy state, so nothing will happen. So ground state atom interact with the reservoir remains ground state and reservoir in the vacuum. However, if atom is in excited state, your system is in excited state, and there is a reservoir is in vacuum. When it interacts with the vacuum, there is some probability. There is some probability that this excited state atoms goes to the ground state, adding a photon in the reservoir mode. or there is 1 minus C probability that atom remains in excited state and reservoir remains in vacuum. So this is a transformation. This transformation shows that there is this transformation shows the interaction of a quantum system with the reservoir modes. What is this P? What is this probability? This probability is 1 minus e raised to power minus gamma t. At t is equal to infinity, this probability becomes 1. So at infinite time, your excited state atom will come to the ground state. And this probability is calculated using Markov approximation. What is this Markov approximation? Markov approximation says that when your environment is very big, just like a sea. You put some water in the sea, nothing will happen on the sea. So environment will not change, and there is no feedback from the sea to the system. So when some information goes from system to the environment, you cannot get this information back from the system, from the environment to the system. This is we call it as Markov approximation. So mostly your reservoir are big enough. It has reservoir have infinite number of modes. When the system interacts with the environment, your information get lost in the environment. Gamma is decay rate, or the atom decays. Atom or system, if it is photons, then it is photon decay rate. In this Markov approximation, this gamma is constant. For example, if you have qubit, this qubit decays. When this qubit decays, it gets entangled with the environment. When it interacts with the environment, it loses its coherence, it loses its purity. This is a pure state. When alpha square plus beta square is equal to 1, it is a pure state. When it interacts with the environment, purity get lost, coherence get lost, and this is with this probability, and this probability goes to 1 when t is equal to infinity. At infinite time, this qubit will be end up at B, at ground state. What about entanglement? There are some questions. We know about qubit. Qubit will end up in the lower energy state, lowest energy state, in the ground state. What about entanglement? How does the entanglement of the two qubit system evolve? Whether it evolve in the same way as the single atom or single particle? While local decoherence rate is related to non-local disentanglement rate? This is a question. Local decay is the same as the local disentanglement rate. Does it mimic the asymptotic decay of each qubit disappearing? Just like we know that one qubit disappears when t approaches to infinity, whether the entanglement follow the same behavior, or it disappears at some finite time. There are questions. I will try to answer this question in the coming slides. In the first slide, I showed that concept of entanglement sudden death. Entanglement sudden death means that there is some probability that entanglement disappears at some finite time. So this finite time disappearance of entanglement, we call it as entanglement sudden death. It was first proposed, this idea was given by U.N. Berlin. They mathematically showed that entanglement qubit decays exponentially, while entanglement may decay, and it may not decay sudden death in finite time, or entanglement may decay in some finite time. If entanglement decays in some finite time, we call it as entanglement sudden death. Here we explain the sudden death phenomena using two atoms. There are one atom, there is another atom. These atoms have their own environments. So this is the environment of atom 1. This atom is in cavity A. The atom B is in cavity B. So two atoms in two different environments. The state, let's say this is the entangled state. Both atoms in ground state and with some probability amplitude alpha, and both atoms in excited state with this probability amplitude beta, which for atom some phase. Now we will calculate how this entanglement behaves when it interacts with the environment. Follow the same transformation of one qubit. One qubit decays in this way, ground state remains in the ground state, vacuum remains in vacuum, while excited state follows this transformation with probability P, it goes to ground state, uh, having a one photon in the reservoir, this probability it remains in the excited state and no addition. And by using these transformation, when we substitute in the state, in this state, this transformation B1, B2, A1, A2, when we substitute this in this equation, and when we calculate the concurrence or entanglement, we get this relationship. C is the maximum, concurrence is the maximum of eigenvalues in descending order. So we sum up all the eigenvalues in descending order, we end up with this relationship 2 into 1 minus p beta and common. So this is the relation. Now we analyze this relation. In this relation, we see that when beta is less than alpha, entanglement disappears only when individual qubits disappears. Under this condition, it is asymptotic decay. However, when beta is greater than alpha, this beta is greater than alpha, it means alpha or beta is less than 1. For this case, entanglement disappears at some finite time. So under this condition, you see what is alpha and beta? Beta is the probability amplitude of both the atoms in excited state. When beta is greater than this alpha, so your contribution of this excited state, doubly excited state, is more than the probability amplitude of ground state. Then in this case, we have certain depth of entanglement. And under this condition, we have certain depth. Entanglement disappears suddenly. Now, this is the case of pure entangled state. This entanglement sudden death is for pure entangled state. What happens? Now, there is some question we addressed. What happens with a mixed state? Can a general two qubit? Because it was a case. It was Harosh paper was a case of a doubly excited state. It has entanglement sudden death. What about other states? What about general entangled state? So we try to answer these questions out here. What about mixed state? If already we have mixed state, whether this mixed state has entanglement sudden death or not, whether this general two qubit entangled state has certain depth or not, we will see. I will calculate this certain depth of entanglement for various environments. Environments may be vacuum or thermal or squeezed vacuum states. So various kind of environment we will see.
Firstly, we assume entanglement state, but we can take another entangled state. The condition is true for each entangled state.
Conditions depends upon the probability amplitudes. What are the probability amplitudes? For two qubit system, we have four possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. Right. So what are the probability amplitudes in each one? The Davidovich paper, he used entangled state of 0, 0 plus 1, 1. He used the probability amplitude with 1, 1 is equal to beta. Probability amplitude of 1, 1 is beta. And with 0, 0 it is alpha. He used particular entangled state and showed that this probability amplitude, when this beta is larger than alpha, we have certain depth of entanglement.
All of them are in the exact state. The entanglement in the state. But one of them is in the ground state and the other in the third state. and we can accept this and kind of entanglement. What happens?
Your answer will be given here. A general two-qubit entangled state. Right. I will consider a general state in answer to your question. Here I will use mixed state. The state already it is mixed. What happens? This is the schematics. Atoms trapped in cavities. We have two atoms. Excited in state, we are trapped in cavities. Each cavity has its own vacuum. So we have all states. This A1, A2, A1, B2, B1, A2, B1, B2, these all states. But we consider a specific X states. Why we consider X states? Finding concurrence and finding other things are easy in X state. Later state later we will calculate the entanglement for all the elements. So if we have this entangled state, okay, among these two atoms, there are various possibilities. There are various conditions. If we have, you cannot see the mixed state over here. If we have initial this mixed state, we see the dynamics of this mixed state. We see that this mixed state has certain depth of entanglement. Similarly, this mixed state has certain depth of entanglement. This shows the disentanglement. This shows the disentanglement. So these mixed state, which has doubly excited component, always show certain depth of entanglement. Now we see that what happens if we have generalized all 16 elements. If you have all 16 elements, what is the behavior of this entangled state? Among these 16, we consider partly one by one. If we have this entangled state, doubly excited component has alpha 1. So, we write this entangled state. Okay, I did not write over here. Alpha 1, alpha 2, alpha 3, alpha 4 with all these components. If we see the disentanglement of this state, which has doubly excited component, we see certain depth of entanglement. This red portion shows that we have certain depth of entanglement. However, if we have A1, B2, B1, A2, see, it is exponential decay. So from these, we calculate this CP, this analytical expression of this entanglement of this state. It shows that entanglement decays when alpha 1 is less than alpha 4. This alpha 1 is less than alpha 4. It decays exponentially. And this white line over here, this portion, is alpha 1 greater than alpha 4. This alpha 1 is when greater than alpha 4. Behind this white line, we have red portion. So this is the portion, this portion shows entanglement certain depth. While in this case, here we see that concurrence has exponential decay. So this entangled state, which have one excited and one ground state, it decays exponentially, while this entangled state, which has doubly excited component, it has some finite time disentanglement. In thermal reservoir, this is in vacuum reservoir, and this is in thermal reservoir. In thermal reservoir, if we increase the temperature, this is for zero mean photon numbers. It decays exponentially. As we increase the temperature of the thermal reservoir, we have finite time disentanglement in both the cases, as well as in this state and this state. So entanglement dynamics, number one, when alpha 1, the probability amplitude of the doubly excited component, it has larger value, we have certain depth of entanglement. If the environment temperature gets increased, we have certain depth of entanglement. So entanglement goes to zero at some finite time. Now there is another way. What happens when the atoms are close together? When the atoms are interacting with each other. Earlier, I considered atoms are separated, atoms are far apart. When atoms are far apart, they do not interact. When the atoms are close together, they interact with each other. So excited state becomes ground state becomes excited state. There is some dipole-dipole interaction among the atoms. So this Hamiltonian, because there are two atoms inside a cavity, and these two atoms are close together. Close together means they interact. The dipole-dipole interaction. There is a dipole-dipole interaction. This shows that there is a dipole-dipole interaction among two atoms, and this shows the decay of the decay of each atom. So this is the decay of each atom. This is dipole-dipole interaction among. So the solution of this is a bit complicated. However, I have some analytical results. If you consider this is state A1, B2, B1, A2, this is the state. Concurrence is this one. Expression of this concurrence is a bit complicated. I have plotted this one. This plot shows that we have, for this state, we have asymptotic decay of this. And the distance between two atoms is very less. It is 0.05 lambda, n is 0.1, it is thermal photon, and phi is 0. So, however, alpha is 0.9. If alpha 2, this alpha 2 is at highest value, we get this certain death of entanglement over here. Even in the case of closed atoms. This 2D plots shows that we have isolation, oscillatory behavior of entanglement. This oscillatory behavior, the straight line shows that entanglement goes down, appear again goes down. So in case when the atoms are close together, we have sudden death of entanglement, then sudden birth of entanglement. So entanglement collapses and revive. So there are collapse and revival of entanglement when the atoms are close together. And this is reason is the atoms are interacting with each other. Entanglement, they are entanglement changing. Why it is changing? Because we have this eigenvalues as the cause and sign function. It is mathematical, but physically, excited state becomes ground becomes state becomes excited state. So there are some oscillation among the atom itself. These oscillations changes the entanglement. So there are some oscillations in it. Because of these oscillations, entanglement has some oscillations. Here you see that entanglement has some oscillation. And this oscillation, this red part shows that it gets destroy and reappear. And if it is phi is equal to pi and phi is equal to 0, it's phi is equal to 0. We have a lower amount of entanglement. For phi is equal to pi, we have higher amount of entanglement. So it depends upon the phase sector also. This it is very clearly shown over here. Entanglement goes down, disappear, and it appears again, right? So for lower value of alpha, for higher value of alpha, we have entanglement loss. So this plot shows that when the atoms are close together, they are interacting with each other. We have oscillatory behavior of entanglement. It shows that entanglement disappear over here, it appear again. Disappear, it appear again. So entanglement, and there is another reason why it appears and disappears, because there are two eigenvalues of concurrence. In concurrence, we have two eigenvalues. One, in some case, this one eigenvalue becomes 0, it becomes greater than 1. So we have combination of two eigenvalues. Right? Because of these eigenvalues. Eigenvalues are oscillating. One becomes negative, other become positive. So our definition of this concurrence is we use maximum first, and then we subtract the others. Well, but the physical reason is interaction of atoms with each other. If atoms get separated, we do not get this oscillatory behavior, this sudden death and revival. So I did not talk about the reservoir. I talk about the atoms interacting with each other. So here I showed that entanglement, there is some finite time, finite probability that entanglement may get disappears, entanglement decays. So in the quantum computation or some any other quantum gate operation, teleportation or some other, we need entanglement. And decay of entanglement destroy our procedure. So this entanglement, we should have some schemes, we should have some protocols to improve this entanglement. So here I showed how we can protect and enhance entanglement. Is it possible to protect the decay and to enhance the entanglement? So here are some schemes. We can protect, we can enhance entanglement. Yes, because of local operation, entanglement, we have two qubits, one with me, one with others. I can perform local operation on my qubit, and local operation may increase the amount of entanglement. So local operations are allowed. And other thing is environment engineering. We can engineer the environment. If it is vacuum, if it is thermal, we can cool it to increase the number of photons. So there are several ways integrated two ways: local operations and environment engineering. So if you consider this state, this is the work of Rose and Ali. They use this one and they operate local operations. What they did, what is the basic algorithm of doing this? This is the density matrix. This is the state, two qubit state. It has all the elements. This is the initial state. This initial state when interacts with the environment. This is a time-dependent density matrix element. When it is allowed, we can operate some gates, quantum gates, on one qubit or both the qubits. Let's say we operate a qubit X gate at times T naught. So this density matrix element gets changed with this one. These are the changed density matrix elements. When this interacts with the environment, this is the density matrix element. So we started with this density matrix. We go there, or we have local operation over here, and we come here. So at the end, we have this density matrix, and this is the concurrence. So we operated concurrence over here. So this equation shows that this is the concurrence when we have local operation. What is the behavior? When this red line shows the green, this shows, black line shows that we have sudden death over here. But local operation at t is equal to t naught, even at t is equal to t naught, local operation means excited state. We started with both excited state, we have a sudden death of entanglement. But local operation means we change the entangled state. When we change the entangled state, the sudden death may be changed to the exponential decay. Here, sudden death is changed to the exponential decay. So changing, operating a local operation on one qubit can change the behavior of entanglement, disentanglement. This is the case of X gate on one qubit. This is the case of double X on both qubit we have operated. What happens when we operate NOT gate on both the qubits? What happens when this alpha becomes alpha 4 becomes alpha 1. So this swapping occurs when we operate X gate on both the qubits. However, if we have, I have talked about it, no. This single path switching, both path switching, cavities on which the atoms are there, they are situated, they are put on the path. We can control the temperature. If we change the temperature of the bath, so entanglement may get changed. At this time here, we have sudden death here, but here we change the bath. Changing the bath means we delayed the death of entanglement. Here, changing the bath means at this point we change the bath. It means instead of having sudden death, we have exponential decay. So changing of bath or changing of applying gates, we may change the entanglement dynamics. For closed system, changing the phase sector changes the, we see that for phase equal to pi, we have this entanglement, for phase equal to pi, we have this entanglement. So if we apply a phase gate on 1 qubit, we can change the entanglement. So these are some techniques. We may apply X gate, NOT gate. We can apply NOT gate on single qubit or NOT gate on the both qubit. We can apply both bath changes on one or bath changes on both, or we can apply phase gate on any one of the qubit. So these are the techniques which modifies the entanglement. If you have this state, one mean A, one is actually, what is one? One is doubly excited state, right? One is doubly excited state, right? One is doubly excited state. If there's some probability with one and one minus probability with four, doubly ground state. For this state, we have certain type of entanglement. We apply X gate on 1 qubit at this time. This is a decay rate. Atoms are close together here. When we apply a gate, X gate over here, entanglement get increased, and you see that stable entanglement get increased. If we apply X gate and Z gate, X gate on 1 qubit, Z gate on another qubit, again we have enhancement. Z gate, by applying Z gate, entanglement get enhanced, and by applying X gate, entanglement get increased. So by applying X gate and Z gate, we may have increased in entanglement. So we may have some operations, we have some windows after maybe some microsecond or some nanosecond, we apply these gates. We keep on applying these gates. So these gates, when you apply these gates, it increases the entanglement. Environment engineering, when we talk about environment engineering, one way of is changing the bath or reducing the temperature of the bath. Another way is to change our dynamics from Markovian to non-Markovian. Markovian dynamics is shows that when the atom decays, the information gets lost. Non-Markovian dynamics suggests that information can be retrieved back. So there, we may engineer the environment. We may engineer in such a way that this non-Markovian dynamics we can change to the Markovian dynamics. How we can change from Markovian to non-Markovian? This is a basic theory. How it works. This is a single two-level atom. It interacts with the environment. So this is the density matrix which governs this equations. So what we do, we take an integrate, we take integration of this and substitute over this. Take integration, substitution over here. So this is the equation after integration. So this becomes the equation, right? When we substitute this equation over here, this is the equation. And this equation, it is a bond approximation that your system and your reservoir are separated. There is it is separated bond approximation, and this is when we solve this one, we see that here this rho s is time dependent. Your rho s and rho r, when we apply this bond approximation over here and we substitute it over here, you see that your reservoir is on initial mode. Reservoir does not change, it has infinite number of modes. Reservoir does not change, but your system is time dependent. When system is time dependent, this is time dependent, integration is hard because there is taking integration is hard. We have to apply some approximation over it. What is the approximation over it? This time t prime is t, because we cannot get back the information from reservoir to the system. When this t prime, we get this t, so it makes our life easy, and we get this this equation. So this is Markov approximation. Under this Markov approximation, we have all these solutions we have shown earlier. Under Markov approximation, this is the decay rate, right? Atom interaction with this, when we calculate this mathematics, this Hamiltonian, this state vector, Schrödinger equations, we solve this in Schrödinger equations. This is the solution. This gamma is constant. This is the value of gamma. So this is the master equation under Markov approximation. So gamma here is constant. Gamma is constant under Markov approximation. What happened when we have, instead of this decay in vacuum, we have two more cavities. Two more cavities means we are confining number of modes. Earlier it has infinite number of modes. Now we have these two atoms in a cavity which has finite number of modes. When the atom decay inside the cavity, when this cavity has finite number of modes, there is some probability this atom will get, this grounded atom will get back the excited state by absorbing a photon from the environment. So this cavity has some decay rate, right? There is some field inside the cavity, atom is placed over here. Now, when we solve these equations, see it is, this is the equation. Now, this CT, we define a function in the cavity, these two cavities. These two cavities has a, instead of having infinite modes, they have finite modes. And these finite modes are defined in this way. So there are some finite modes, and this is the mode distribution function, JW. Well, there is some mode distribution inside the cavity. So there is, and under this condition, there is some probability that atom will get information back from the environment. So when we have this finite mode inside the cavity, and when we solve these equations, CAT, this is the probability of finding finding the atoms in the excited state. This comes as this, called hyperbolic function, sine hyperbolic function. And the gamma here becomes the time dependent. Decay rate is not the constant now. Decay rate becomes a function of time. So this dynamics is non-Markovian dynamics. What we did instead of decay of atom in the environment, open environment, we confine the environment by placing cavity over here. So placing cavity makes gamma is time dependent, and gamma is time dependent. This is the field inside the cavity. This gamma T is this one. So instead of, so this is our earlier paper. Now we designed that we put this inside a cavity, another cavity. These atoms are placed inside a cavity. We calculated the entanglement dynamics of two atoms in the reservoir. Now these two atoms are in the cavity. Cavity has this mode function. Instead of infinite mode, it has this mode function. And this mode function shows that earlier psi plus minus green line shows that this is dynamics of non-Markovian. Markovian dynamics. This red one is Markovian dynamics of phi 1. When we insert cavities, the dynamics change. The psi plus, earlier this green one becomes blue, and this red one becomes this one purple. So this dynamics, decay of entanglement, get changed simply by inserting cavities. The 3D plots, you see that Markovian, this purple part, this part shows sudden death of entanglement. This is the decay. So sudden death of entanglement decreases if we have Markovian dynamics. So this is the comparison between Markovian and non-Markovian dynamics. Where for different cases, for mixed state, we compare different cases. In each case, Markovian and non-Markovian, we see that in case of non-Markovian dynamics, entanglement, sudden death, less value. entanglement degradation is less on all these cases. Effect of system environment coupling on bipartite system in structured reservoir. In the structured reservoir, this if we have a single cavity, entanglement gets increased. So this is the case of A1B, A1, B2, B1, A2, and this is W excited state. For the case of W excited state, we have this entanglement dynamics, and the atoms are in cavity in this mode, and here we see that entanglement in both the cases get increased. When we have separated cavities, we have single cavity and two atoms. What about quantum beat laser? In quantum beat laser, we see that we have some entanglement decay in each case, but we inserted cavities. So there are two modes there. In the two modes, above all, these two modes insert a cavity. In the insertion of this cavity, limit the number of modes in the environment. So what happens with the mathematics? This is a rate equation, and the output is all mathematics. It shows that your entanglement, which was earlier function of n bar, u, and tau, and omega, this is now a function of this delta. So earlier you have entanglement, decay. Now you have oscillatory behavior of entanglement. So entanglement get increased even in case of 2-bit quantum beat laser. Here I showed that Markovian and non-Markovian dynamics in case of non-classicality. If you change the non-classicality is high, entanglement is high. Non-classicality get decreased, entanglement get decreased. So in non-Markovian, it is enhanced. Same scale, but the entanglement is enhanced in non-Markovian dynamics. Changing Markovian to non-Markovian is very trivial. Just insert another cavity. In my earlier talk, I plot this one with respect to squeezing. When the squeezing is high, entanglement is high, it is 0.4. The squeezing is less, entanglement is less. So it is Markovian dynamics. In non-Markovian dynamics, if I insert a cavity, this entanglement gets increased with same squeezing. In case of thermal noise, this is Markovian and this is non-Markovian dynamics for various values of average photon number. Driving field strength, it depends upon the driving field strength. Again, it gets increased. So it clearly shows that entanglement gets increased in non-Markovian dynamics. What about in quantum beat? In quantum beat lasers, not quantum beat, quantum dots. In the case of quantum dots, this black line shows this entanglement in Markovian dynamics, and this red one shows entanglement in non-Markovian dynamics. So we see that in each case, whether it is a quantum beat laser or it is atoms or any other system, in non-Markovian dynamics, entanglement get increased in each case. This entanglement engineering kind of thing, these are my collaborators contributed in Markovian to non-Markovian dynamics and entanglement dynamics studies. Thank you very much.
Do you have any questions? No question. Thank you very much. Thank you very much, Rajat.
Tomorrow Tomorrow I will talk about the research activities, the technical on the experimental side, what we are doing at NALO. So my 3 talks were on theoretical side. Tomorrow I will talk on experimental side.